Is contemporary physics wrong?
It's not wrong. It's wrong as an opinion. It's irrational. And that's a different standard. We have objective standards for what is rational and subjective standards for what is correct, incorrect, true, false. Those are opinions.
Why is contemporary physics irrational?
Okay. Which is a different kind of question. It's irrational because the explanation, the physical interpretations that the mathematicians, I don't call them physicists, I call them mathematicians, what they offer for the phenomenon that we observe are not even within common sense. And this is not my opinion, by the way. Conference I gave yesterday, I showed that even the Nobel Prizes, the people who created quantum mechanics, they say that they don't understand their own theories. So obviously something is irrational if they can't understand their own theories. So it's not me that's just saying this.
But general relativity and quantum mechanics have been proven by experiment. Are you saying that most of the scientists in the last 100 years were and are wrong, irrational?
What we're saying is that the explanations that they offer are irrational. And yes, science unfortunately is not democratic. We don't get to vote for theories because that's religion, that's opinion. In science we only explain and understand. Once we're finished with the explanation and understanding part, we're finished with science. And what we don't have right now is rational explanations for the phenomena we observe in laboratories and in the field. So there are no rational explanations. And yes, if all the people in the world, all the mathematicians in the world believe or propose the flat earth society, the flat earth theory, not because they all voted for it does it make it right or does it make it rational. Maybe it's right for them, but it doesn't mean it's going to be rational. It doesn't mean that they have explained how this universe works.
Thanks for this interview.
What is time? We all gain time, we all waste time, and we need to know what it is that we're wasting, right, or gaining or whatever. Time has been with us probably as long as we can remember. One question that arises is whether animals know about time. And the reason I ask that question is, could it be that our ancient ancestors, thousands of years ago, did they know about time? Did Neanderthal man know about time? And I have an idea that, or my notion is that they probably knew a little bit about time. We all have this intuitive notion that night turns into day, winter turns into summer. You look at the lion. I was telling someone here, the wildebeest go around, they do their yearly cycle. Is that the lion's clock? They know it's time to go hunting again. The wildebeest are coming. Is this their clock? Do they have intuition about this? Some people study this, and they say there is I can't remember the term, but it's like biotime. They look at all the repeatable things in nature, and they say, yes, animals do have some sense of time. And that's probably where we started with our notions of time. Then we went a little more specific. We started inventing clocks. Calendars. This is the upper one. I don't know if you are able to see it very well here. That's the summer solstice in Chichen Itza, the Mayan culture. And they were so concerned about when, summer came again, that they built this pyramid in which you can see, as soon, this is real time, you can see the sun coming in there and drawing that, what you see there, that's the serpent. It's the serpent. Once the sun touched the nose of the serpent, summer was here, officially. You probably heard about Stonehenge, same thing. They waited for the light to go right through there. They developed this by trial and error. They said, oh, every time, we have something, the summer solstice, sun comes here, so they built a stone there, and here was the sun coming through. And they set that as a marker. So we invented calendars, and you ask, well, what is a clock? Because that was the next step. Well, a clock is a fast calendar. And a calendar is a slow clock. That's all it is. One measures time in years, months, weeks. The other one measures time in hours, minutes, seconds. So we invented clocks. Some of the first clocks we invented were the sun clock, it's called a sundial. And the other one was a water clock. This one's running a little fast here. It was really dripping. They would drip one drop at a time, and it would fill another bucket that had lines on it. And when it reached a certain level, you knew 15 minutes were up. What did we use this for? You're going to laugh. The Greeks used it to time patrons who slept with their prostitutes. They say, your time's up, buddy, out. We got another guy waiting. The Romans, Tacitus tells us this. The Romans used it to time their politicians. You had 15 minutes to make your case, and then you're out. So they would time it. It's called clepsydra. Clepsydra was a water clock. As soon as the last drop fell, that was your time was up. 15 minutes approximately. And, we moved our way all the way to fast clocks. Now we measure time with all these different kinds of watches and clocks and things that we've invented. So what came next? What came in the 20th century? Well, what came into the 20th century was something different. We entered the twilight zone. We went into special relativity. Suddenly, we forgot about clocks and calendars, and we started talking about time. Clocks, the device that you used to measure time was no longer so important as time itself. Time took center stage. And the man behind it was obviously Albert Einstein. He's the one who made the main revolution. And I'm going to criticize some of his theories. What am I going to criticize? I'm going to criticize that time is not a physical object, as special relativity and general relativity say. Now you're going to say, you're crazy, Bill. What do you mean? General relativity doesn't say that. Yes, they do. They do either directly or indirectly, or implying that that's what it is. They say time was created at the Big Bang. What did they create? They created something, hopefully, right? So they're treating it, so even though they may not officially say, look, it's a physical object, they're treating it as a physical object. What can you create other than a physical object? Something. They say you can travel through time. Have you ever tried to travel through width or through height? Can you travel? Is this a tunnel of some kind? You travel through it? You travel in it? No, we travel to objects, not through time. Time is not a medium, but they treat it as such. They say time can be molded. They say gravity can affect time. They talk about time dilation. They're treating it as a physical object. And they say that time moves in a given direction. They say time moves forward. So they are, in effect, treating time as a physical object. When you say, hey, you're saying it's a physical object, they'll say no. But in every one of their statements, they are treating it as a physical object. I'm going to challenge the notion your twin brother can be older than you, much older than you, 3 times, 4 times as old as you. I think this is nonsense. And I'm going to challenge the notion that global positioning system, also known as GPS, confirms relativity. It does not, and I'm going to show that today. And at the end, I'm going to try to give a definition of time. What is time? Let's go first through general relativity, and then maybe we can end up with what time really is. We have a defender of relativity. He's a very popular presenter. He's the guy, I guess, who replaced Carl Sagan. Some of you probably heard of Carl Sagan. And Carl Sagan was a good presenter for general relativity and mathematical physics in general. And this is his follower. He's the guy who came right after him. He's the one who does a lot of TV shows for Discover and all these other programs, all these, what do you call it? Yeah, the Discovery Channel, all these channels, right? What does Brian Greene say? Well, he said all these statements are taken from a YouTube video. That it's on the YouTube. He did it for television. They put it on YouTube, and you can check each one of these statements. The Big Bang is what set the arrow of time on its path. The explosive force of the Big Bang sent space hurtling outward, and as a result, the universe is still expanding today. Now, he's talking about the arrow of time. He says the Big Bang is the origin of time, among other things, like space-time, right? He's saying that it's also the origin of time. So that's the starting point, right? And this is how they present it. This is known as the Big Bang. Here you have a dynamic version of it. Here you have a static version of it. What is it? It's something, we have nothing. And suddenly a little light appears, something appears. It just gets bigger, bigger, bigger. And we arrive till today. If this is the origin of space and time, we're moving in this direction. And this is the present. This is today, which is approximately almost 14 billion years ago, I think. Stephen Crowther's mentioned 13.8. I was a little behind the times at the time when they did this. It was 13.7. So now we're a few billion years older, I guess, right? Okay, this is the theory. There's been some kind of explosion. There was nothing. Suddenly something appears. No God, no anything, just spontaneously, poof. You know, the rabbit appears on its own without even the magician. And it grows, and that point is that point there. So what does a rational person ask? Well, a good question is, what came before time? What's this black stuff here? What's this black stuff that surrounds space, time? So what is the answer that relativity gives to this? Well, the answer that, they give you two answers. They've got this already figured out. They've already memorized the answer. And they say, it's an irrational question. Oh, irrational question. Yeah, it's an unscientific question to ask what's out of space, time, or space-time. You say, why is it irrational? Because it's like asking, what is north of the North Pole? You'll find this kind of answer constantly. Well, very easy. Or north of the North Pole, you know, that's where Santa Claus is, right? North of the North Pole, we have space, and we have Polaris. We have a lot of stuff. South of the South Pole, we have space. East of the East Pole, we have space. West of the West Pole, we have space. We have space all over the Earth. Every single atom in the universe is covered by space. You can't say that, you can't say this about space-time. Because space-time, this little bottle here, that's what we have, right? Right? Well, this includes space, time, matter. It's all in here, in the little bottle, in the little glass. Oh. Okay? This includes space, time, and matter. So if this is space, time, and matter, what's the black stuff? It's a valid question. You can't say what's north of the North Pole because this is their theory. They're the people who are going to have to tell us what they propose in there. What do we have there? And the other issue, the reason they can't say that there's nothing there, is that they talk about the multiverse. I think Steve mentioned a little bit about that. Ours is only one universe. There are many universes. So the universe looks more like this. The universe they're proposing, right? That's the multiverse. That's our little universe there. That's ours. All the others are other universes. They're connected by wormholes. So now the question is valid. What is this black stuff that divides all these universes if this contains space, time, and matter, and thought, and everything you can think of? So it is a valid question. It's the hypothesis that is wrong. The presentation starts out wrong. They can't continue to their theory because they haven't even begun rationalizing what they're proposing. So that's where it fails. Well, he says that we can absolutely travel to the future. He says that we can travel through time. That's the second issue, right? Again, he's treating it as a physical object. He says you can travel through this tunnel, time tunnel, wormhole, whatever you want to call it. We can travel through it physically. He said, we can absolutely travel to the future. Look what he's saying. You can travel to the future. You can see your great-grandchildren today. What's the limitation? What's the problem? Well, the problem is, if you want to see what things are like 1 billion years from now on our planet, right? Einstein laid out a blueprint. He showed us how to do that. You build a spaceship that goes near the speed of light. We can't do that yet today. That's a technical detail. It's just a petty thing, just got to build the right spaceship, but then it's easy. He said it's easy to go to the future. Now, isn't that wondrous? You can go see your great-grandchildren. The question, why don't our great-grandchildren come and visit us? No one has come from the future, right? You would think they're more technologically advanced. Maybe we can't go forward. Maybe they can go backward, right? Well, he says they can't. We can absolutely go to the future, but we cannot, as far as we know, go to the past. That's still out there in left field. We still have not proven this, right? And so how do we get to the future? Well, there was a French philosopher known as René Descartes, and Descartes was probably the first one to propose discrete units of time, which is what today is known as the chronon. It's a particle of time. He's the one who suggested time is divided into little pieces. Newton said, well, not really. Time is more like a flowing river. It's continuous. And now comes Einstein, he says, they're both wrong. We're going to freeze the river. We have a frozen river, and we're just going to walk to the future. That easy. It's a piece of cake. And he walks it. He's walking to the future. Isn't that great? Now, how much of this is science, I don't know, but this is what they're saying. They illustrate it. So if you don't understand this, I don't know. We're done. How does he get there? Well, he first comes up with what is known as the block universe. We have a universe, it's divided, each one of these little lines that you see there, each one of those is the universe with everything in it. Matter, except time. You have matter, you have space, everything. And as we go forward, we have time, okay? He turns this block universe into a loaf of bread. And he cuts the loaf of bread. He cuts it for us. He takes his laser pointer and he slices it, right? And he can do that with any slice there. So we have the past, the present, the future. You can see any slice you want. That means if you want to go, say, to visit Napoleon, right? Well, you don't only move from here to Waterloo, Belgium. You have to go to a different slice. You have to go back here somewhere. So not only are you moving space-wise along the slice of bread, you have to move to a different slice. You have to do both, space, time, okay? So what are we doing? We're saying that this is really a movie. It's some kind of movie that we're looking here in one piece. It's like he took this whole movie and turned it into a loaf of bread, okay? And here you have the past, the present, the future. This is how, here's another vision of that. Past, present, future. Each slice is the whole universe. And what we're looking at is the position or the location of every bit of matter from one second to the other. Okay? That's what they're trying to tell you here. So how does he do it? Well, he illustrates it. He buys a ticket with a rocket to the future. And he leaves. He comes back, right? And when he comes back, the check-in agent has aged. Now, that wasn't the surrealistic part for me. For me, it was surrealistic that he found a check-in agent. We're replacing them every day with machines. Go to the airport, you find machines. You can't find a check. After 50 years, he finds a check-in agent. And the airport is empty. So I don't know how he did that. That is surrealistic. But he says, if I spend an hour or two in orbit, something like 50 years will have passed back on Earth. Now, does that sound intuitively logical? Well, intuitively it doesn't, but they say mathematically it's correct. Okay, so let's look at the mathematics. Let's see if the equations, all that, support this, right? If you want to go to the future, if you want to go to the past, there's a little trick here. And again, they don't know if they can do this. he jumps into a wormhole, and he visits himself a few minutes earlier. Okay? To the future, it's easy. Just take your spaceship, go forward, come back, everything has aged on Earth, and you're still young. And if you want to go to the past, you got to jump into a wormhole. And if you look up a fellow named Michio Kaku, he tells you how to build one of these wormholes. So get ready for it. You know, we're almost there, right? We're almost in the future. Okay, so if you want to visit Napoleon, rational person asks, do Mickey's arms on your little wristwatch, while you're in the time tunnel, you're in this wormhole, and you're traveling to the past, does the arm on Mickey's arm go backwards? I mean, you would think that when I was a baby, that watch would show, I don't know, in my case, 62 years ago, right? It goes backwards. Does it do that? By what physical means? I mean, okay, I'm moving through the tunnel. I'm going to the past. I'm going to shake hands with Napoleon. Did my watch go backwards? Yeah, but we have to explain it. Would the clock, would a clock or a watch or whatever, would it go backwards? Yeah, go ahead. Not only that, let me also add to that. If you want to go see Napoleon, right, 200 years ago, Battle of Waterloo, 1815, every piece of matter has to be moving backwards through each one of those slices. You're going 200 years into the past. So hopefully every bit of matter, the sun has to go where it was then, the Milky Way with respect to the Andromeda galaxy, everything has to be turned back. So is the Earth, as you travel through the wormhole, is the Earth going in the opposite direction to help you? You see the problem? And the alternative is something even worse. What we're saying is that God has this big file cabinet with each one of the universes there. He says, where do you want to go? Well, I want to see Napoleon. Oh, okay, let's see. Here's the file. Here's the file in the cabinet, and you go and visit them. I mean, why would he keep all this? Doesn't God have better things to do? You would think so. General relativity is a gravitational theory, but general relativity uses space-time. It has also, factored time into the theory. Now, how do we get to special relativity? Well, if you take your ironing board and your iron, and you flatten space-time. Remember, according to general relativity, gravity is the curvature of space-time. You have curved space-time. You have this curved net. Everything falls in it. That's gravity. But what if you take your ironing board and you iron out space-time? Now you've got a flat surface, right? You've got something that looks like this. Yes? We flattened space-time. Now we have no gravity. This is the world of special relativity. Special relativity is general relativity without gravity. Okay? That's the world we have. The world of special relativity is the world of flatland. In flatland, the squares, the circles, they don't suffer gravity. There's nowhere to go. I mean, you can fall down the stairs. They can't. There is no down. Okay? And you can't fall sideways. So special relativity is flatland. This is the world that they propose. You remember this, the Flat Earth Society? Any of you belong to the Flat Earth Society? We have this flat Earth here, right? And they say this is wrong. What is right is this. The world of ours is flatland. Said based on the WMAP, some of you are aware, Stephen Cross talked a little bit about that. They may take all these measurements out there, right? WMAP says that we now know that the universe is flat. We live in a flat universe. This is our universe here. Our universe is not round as Riemann told us. It's not a ball. It's not a saddle like Lobachevsky told us. No, it's like Einstein told us. It's a flat universe. You think I'm kidding. You say, you're exaggerating, Bill. Am I? Let's find out. So this is our universe. Astronomy magazine. That's our universe. And the question always pops up, what's this black stuff that gives shape to our universe? If this contains space, time, and matter, what is this black stuff? It's a valid question. It's their hypothesis, which is wrong from the start. So some of you are aware of what this is. This is the GPS system. GPS is a series of over 30 satellites. And they go around the Earth and they tell you essentially the position that you have on Earth. They can measure that quite accurately, okay? People say, well, GPS confirms general relativity and special relativity. See, it works. Oh, yeah, it works. Does this prove that time is a physical object that you can dilate? Does it prove that gravity, a concept, has the power to affect time, another concept? Does justice affect love? It is a semantic issue. It's also a question of epistemology. What are these people talking about? What do you mean gravity affects time? Well, they say that this would not work if it weren't for time dilation. But one thing is for the clock to run slowly, and another one is to interpret from there that what has happened is that time has run slowly. We're talking about two different things. Are we talking about Mickey's arms, or are we talking about time? See, they've concluded, they've extrapolated that because Mickey's arms run slowly, time is running slowly. And because gravity was the one who caused Mickey to go slowly, well, gravity affected time. It doesn't follow. You see that? We're talking about concepts here. Okay, so let's concede. Let's say that that's true, right? They say that they've measured it with atomic clocks. In fact, they ran a couple experiments. One of them, the Gravity Probe A, run in 1976. Gravity Probe A, they sent one clock, atomic clock, high above the atmosphere. And they left a twin on the Earth. So that they synchronized them, they sent one into space. And they looked, and they said, as it climbed, the clock ran slower and slower. So now they could determine empirically, through the experiment, they could determine where to put the satellite for GPS. They said, well, right here, we know what it's going to read. They had to adjust the clock. So they sent their clocks, and they said, Einstein says, general relativity says, clocks that are close to the source of gravity, the center of the Earth, run slower. Clocks which are up above the atmosphere in space, they run faster. That's what he showed, right? No, we're not talking about motion. That's a good question. Let me clarify that. Special relativity talks about what is called kinetic time dilation. Talks about moving. Here we're not talking about moving. We're saying, what if we put one clock here on the floor and the other one on Mount Everest? They tell you the one on the floor runs slowly, the one on Mount Everest runs faster because it has less gravitational influence. Okay? That's the theory. And they measured it with atomic clocks. And they say it happens to all clocks. Well, I was going to bring my atomic clocks today here, but they took too much space in my van, so I hope you don't mind if I bring my own clocks today, and we do the experiment here with you present, okay? So let's look at this. Let's see if this is true. I brought my own sand clocks, if you don't mind. Okay? Now, this is the right clock to measure gravity with respect to time. This is a gravitational clock. It works by gravity. If you don't like my clock, we can use a pendulum clock. Also works by gravity. Well, this clock runs faster when it's closer to the center of the Earth. And this one runs slow when it's up in space. And you may say, well, I'm not so sure about it. Is that true? Very easy. I take this to zero gravity, not a single grain will fall. Very simple. It'll float in the first bulb here. Not a single grain will fall to the next bulb. We have just destroyed the postulate of general relativity. This clock runs fast, this clock runs slow. It's just as simple as that. In fact, we'll go further. Time dilation means time has dilated, right? Well, now we take this to zero gravity. Time has stopped altogether. Here we have the astronaut. He's holding this up in the air. His blood is running through his veins, but time has stopped because not a single grain will fall. That's their type of conclusion. That's their rationality. That's the type of rationality they apply to these things. Okay, so this clock runs fast. This clock runs slow. So we've now, contradicted the claim of relativity that, clocks which are closer to the center of the earth run slowly. This one runs faster. Let's see if we can apply any of this to special relativity. Here we have the Einstein twins. This is Al Einstein, and this is Frankenstein. Frank Einstein, okay? The two brothers. Well, we send Frank out into space. He comes back. He's still young. He finds his brother has age. His brother's old. Is this fantasy reality? Well, let's find out. Who's right? Is this man's clock right, or is this man's clock right? They both carried atomic clocks. One stayed on Earth. The other one went on a trip. He comes back. His clock says, hey, I only aged, a year. And this guy ages 50 years. And his clock says so. So do the equations say so. Okay, so who do we believe now? Is this possible? Is this science fantasy? Let's find out. Let's find out who is right here. The way we do it in science, we look at the definition. What is the definition of the word year? It turns out the definition of the word year has not changed in years. It's never changed. The orbit of the Earth is defined as a year. These people are using a clock as a calendar. They want to tell you how old you are by counting the seconds on their atomic clock. Well, that's fine if you do it here on Earth, but now you take your atomic clock out there, and we know through GPS that they have to make an adjustment to that stupid clock before they send it out there. That means it's not an accurate clock. It's just as accurate as one of these guys. If we have to make an adjustment to the clock before we send it out, we've got a problem. We've got a problem. We've already dilated time. And they want to tell you how old you are, not by counting how many times the Earth went around the sun. They want to do it by counting the seconds on your atomic clocks. They're using a clock as a calendar. It's irrational, totally irrational. Okay? So this is Einstein's way of measuring the time. He says we take 31.5 million seconds, which is the number of seconds in a year, and we multiply it times the cesium wave, which is 9.2 billion blips a second. Okay? So if you take 9.2 billion blips a second times 31.5 million seconds, you end up with a year, right? Well, that's okay if the clock is sitting here. If we take that clock into outer space, now we have to subtract time from it. That's what we do with the GPS. So we can't use that clock to tell you how old you are. And after they tell you all that, you find out that these guys have no idea what the word time means. They talk to you about 2 hours about time, and they say, okay, well, by the way, what is time? Oh, St. Augustine said, when it is time, if no one asks me, I know what it is, and if I wish to explain it to him who asks, I do not know. And nothing has changed in the last 2,000 years. Here we have Newton. He said, I do not define time, space, place, or motion because we already know what it is. So why should I take the trouble? They never defined a word. And time is an important word in physics, at least according to them, right? And we have two people here. Again, we have Stephen Hawking. You all know him. And we have Paul Davies. They write 2 books, and they never tell you what they're talking about. In fact, Paul Davies specifically, he says, I have no clue what time is. But his book is called About Time. He writes 300 pages, makes a lot of money, and then says, by the way, I don't know what time is. So what is time? Well, after they told you all that, they always tell you that time, that in fact they do know what time is. Time is a dimension. It's the fourth leg of space-time, right? We have length, width, and height, and time. Okay, but can we do that? Can we replace, height with time? Is this an equal type of, can you do that? Can you replace one with the other? Well, according to Stephen, yeah, we can. Stephen Hawking says relativity, there is no real distinction between the space and time coordinates. Now that's something. Why? Because they define it as the minimum number of coordinates needed to specify a point in space. Well, this may be true in mathematics. It's got nothing to do with physics. In physics, we define dimensions a little bit differently than time. What is a dimension? A dimension only has really two properties. The first one, it has direction, which time doesn't have. And let me show that very clearly. I want everybody to point. Please point with your arms. Point. You pointed upward. He pointed in that direction. Where is time? Is time pointing in that direction? Which direction does time point? Please go in the direction of time. You can't, because time does not have direction. Time has magnitude, but does not have direction. And dimensions have the opposite. They have direction and orthogonality. When you talk about length, you immediately are implying width and height. There's no such thing as length all by itself or width all by itself. Width comes with height and with length. Whether you use it or not is a separate issue. So a dimension has direction and orthogonality. It's got perpendicularity. Whereas time has neither, has no direction, no perpendicularity to anything. Time only has magnitude. What are we describing? We're describing a number line. Time is not a dimension, time is a number line. Okay? And here are the differences. A little more specific here. Dimensions are used for objects. They tell you the orientation of objects, how they face, how they're tilted, what face they show you, and a 90-degree angle to that. That's what dimensions do. Coordinates, they tell you about the location of objects. No one confuses a coordinate with a dimension, except relativists. And then we have vectors. We have depth, breadth, and elevation. Those are the three vectors. They deal with motion, with displacement. That's why I drew them with dotted lines. It's motion. You're talking about different location. These are three different concepts. We never mix them in physics. In mathematics, they're all the same. And because they're all the same, Stephen Hawking can tell you, there's no difference between a space and a time dimension. Why? Because they're not talking about dimensions, they're talking about number lines. Number lines are different than dimensions. What are those differences? Differences are the dimensions, coordinate, and vectors are qualitative notions only for physics, right? They have direction and orthogonality, whereas number lines have only quantitative notions behind them. Number line has magnitude but no direction. So whenever they say space-time is four-dimensional, no. Space-time is four number lines. That's what it is. You're saying, with four number lines, I can locate a point within space-time. You're not telling me anything about the object, how it faces, how many faces it has, or which way it's pointing. Okay? So we finally arrive at the definition of time. What is time? Time is the relation between new motions. I have Mickey's arms on my watch, and I have the Earth moving around the sun. The Earth travels at 30 kilometers per second, which is not important, the value. The Earth travels. It covers this distance. We take that distance traveled, and we compare it against the distance traveled by the arm on Mickey's watch. And we say, that's 1 second. We're comparing two motions. Why is this important? In physics, at least, right? Why is this important? Every time you hear the word time, we dilated time, we traveled through time, gravity bent time. You replace the word time with the words that define it, the relation between two motions. Can you dilate the relation between two motions? Can you travel through the relation between two motions? Just replace the words with what it means. And then you'll know whether you can travel through time. After saying all that, I'm going to apologize and say that I actually do believe in time dilation. And I'm going to prove it right now to everybody. Time dilation, here on this here, you want to film it? You'll see time dilation right here and now. Everybody ready? This is a one-time only, yeah? I dilated time. No, wait. My wife sometimes gets very angry at me, especially when I talk about some things that I shouldn't talk about. And what she does, she takes all my clothes, washes it in very, very, very hot water. She produces the opposite. She produces time contraction. Then when I try to put it on, squeezes my legs together. Thank you.